Good afternoon. We finished our previous lecture on the aging process, aging rule process that increases the dynamic part of priority each time a process does not get processor and reduces the priority to base priority when the process gets a processor. So let us imagine that we have 4 processes of the same base priority. And the current situation is that process 1 has the highest priority. So in the next time slice, process 1 will be lowered priority to base priority, and every other process will be raised by 1. And again, now process 3 is the highest priority, and because process 2 was reduced to base priority, and every other process raised by 1, and so on and so on. I made a simulation for 5 processes. 2 of them have base priority of 100, 2 of them 102, and 1 105. And I showed after every scheduler decision the highest priority with the bold font. In a case that 2 processes have the same priority, I assume that the process that is inserted into the queue goes to the tail, so a process nearest the head waits longer. In such simulation, process P1 got a processor 7 times, and P2 as well, P3 and 4 9 times, and P5 on the blackboard 5 times. It shows that this rule of aging really works. It gives more processing time to the processes with higher base priority and less processing time to the processes of smaller base priority. This mechanism is used between minimum priority and max age. Over max age, aging is not used. This area is designed for processes, for real-time processes. And to save time, not to waste time on switching between processes, non-preemptive method is used. That means that, let's look at this point. A process with higher priority than current process it occurs somehow. It is new process or it is woken up by an event, but it does not get priority despite the fact that it has highest priority at the moment. When this process waves from using the processor, a process with highest priority is chosen. This is non-preemption mechanism. When the more important process arrives somehow, but it does not get processor until the other process waves from the processor. The third area is below mean priority. In this area, we have the processes that are scheduled with preemption. We see this, for example, in this moment. No, this moment. Oh, this moment. The process with higher priority occurs, and we preempt current process from processor and give processor to another process immediately. The same occurs here. The process that currently works is preempted from the processor, and a process with higher priority starts to use processor. So it is preemptive strategy. And depending on conditions, we can place our processes in one of those three areas: in aging here, in preemptive here, or non-preemptive here. Okay. This is preemption, yeah, this moment. So we have three strategies in this system. Overmax age is non-preemptive with static priorities, and we do not limit time for a process. In aging area, it is non-preemptive. We have priority with static and dynamic priority, but we limit time for which a process gets processor. Below mean priority, we have preemptive with static priorities and non-limiting time. I imagined how I would run a set of processes in such a system, processes having given properties. Real-time processes with hard constraints, I would run over max age to let them finish their work as quickly as possible. Non-preemptive policy supports this decision because we do not waste time on context switching. A process which gets the processor uses this processor until it finishes. Below max age, but high in this area, I would run real-time processes with soft constraints, because temporarily they can be late on condition that in the future they will compensate this delay. Below those processes, I would place interactive processes that conversate with a human being. They should be high in hierarchy because people do not want to wait long for the reaction of the system. So source code editing should be, in my opinion, here. When we look close into operation of a compiler, it does some calculations. It builds the parsing tree, then it generates the output code. So it is partially a calculation process. However, from time to time, it reads some part of source code, and from time to time, it outputs the binary code on output. So from time to time, it uses input-output. So I would place it over numerical calculations. And numerical calculations on the bottom, because if numerical program gets the processor, it runs as long as possible performing calculations. For example, some simulations. Why do I put data backup? Data backup is generally background process. Why it is so high in hierarchy, in my opinion? Because this program reads, writes, and reads, and writes, and reads, and writes, and almost always this program waits for finishing the input-output operation. It consumes the processor power very little. So, in my opinion, it could be run relatively high in the hierarchy. But financial calculations, they are important. However, it is not important when they finish their work. So they can wait for the time given for those calculations. Of course, I assume that the system is generally schedulable. If the system is not schedulable, we must simply buy another computer. Okay. Let us switch to the next slide set. Which is synchronization. First, we will discuss some possible situations from everyday life in which some synchronization issues occur. For example, it's Polish saying, we are talking and a man picks plums. It says that we must take care about our matters, because if not, someone else can do something wrong for us. Let us analyze the situation. We are talking. Two processes should synchronize themselves to meet at the same time, at the same place. They must prepare some actions to be ready for data exchange in given moment. However, when we take care about our garden, a man cannot pick our plants. He can pick the plants if we are not at the moment ready to defend them. So, a situation in which a man is in the garden and we are in the garden is excluded. It is possible that no one is in the garden. It is possible that we are in the garden, just watching about our property. And it is possible that a man comes to the garden to pick the plants. However, we are outside at the moment. It is mutual exclusion. It never can happen that two persons are in the garden at the same time. Now we have spring, almost. After a few days, we will get to spring. There are no plums to pick because it is spring. We must wait until the autumn. We must wait until the plants grow. Okay, now it's September, for example. And the man goes to the garden and picks the plums. How many plums he can pick? As many as grew up. Not a single plum more. If we have 100 of plums, he cannot pick 101. He can pick 99, okay. But no 200. To get a single plum over the limit, that is the number of plums that grew, he must wait a year. Or he can go elsewhere to the shop. When the plums grew up, again he can go and pick them. Okay. Let us imagine that we have bought a new car. In the evening, we go to the bed. Our car stays in a parking place. So we suddenly wake up and look through the window if the car is still in the position we left. Yes, it is. We return to the bed. And the situation reoccurs because we are afraid if someone could steal our new car. After some non-sleepy nights, we go to the electrician and we buy auto alarm. Well, now every car is equipped with auto alarm. Not strictly auto alarm because it is silent. Those days I prepared this story with students. Auto alarms were installed privately by people because the cars were not equipped with auto alarm in the shop. And in windy night, there was not possible to sleep because all auto alarms were on. And the sirens were so noisy that it was almost impossible to sleep. So a new regulation was established that auto alarms should be silent. They can inform by radio or other means about the fact that something's going wrong. They cannot use sirens. Okay. After buying auto alarm, here I showed mechanical version of auto alarm. We have a wire connected to the car and to our toe. If someone steals the car, the wire wakes up us, and we just run after the thief. This shows a situation in which a process waits for an event. And this event wakes up the process. If you know pipes from Linux, you know that we can write or read from the pipe. An operation write to the pipe is a good example of three phenomena: mutual exclusion, mutual scheduling, and data exchange. When we write to a pipe, first, we are sure that during performing this operation, no other process can run to the same pipe. Operating system takes care about this exclusion. And during this time, no process can read from the pipe. So we have mutual exclusion between processes that access the pipe. Only one of them is allowed to read or write at the same time, at given time. So it's mutual exclusion. If the pipe was empty before our writing, any reading process is suspended because it cannot read from the pipe. After we write to the pipe, a process must be woken up because now there are some data in the pipe. It is mutual scheduling. Like in plums, we cannot get more that is in the pipe. If the pipe is completely empty, we cannot read anything. If we enter 100 bytes, we can read 100 bytes, not 100 at one. And it is data exchange. One process enters data to the pipe, and another reads data from the. So those three phenomena occur in simple writing to the pipe. Problems occur when processes use common resources. In the case of the pipe, there are two kinds of resources. First is the pipe itself. And the second is every cell of a pipe. Every cell can contain only one piece of data, 1 byte, and it is protected from entering a new value before we take the old value from this cell. And the pipe as a whole is protected such a way that even if two processes want to write, the bytes that are produced by those two processes do not interleave in the pipe. The operation write enters to the pipe the coherent sequence of bytes, not interleaving with bytes from other processes. To protect common resource from wrong use, we use some means Halo? Słucham. Przepraszam panią, ale ja mam teraz wykład, może innym razem. No nie mogę teraz, właśnie studentów mam przed sobą i niestety nie mogę z panią rozmawiać. For all those properties, we cannot organize them ourselves, because there are some means in the computer which allow to organize exclusive access to resources, but they are available generally only in system mode. So a program cannot do it itself. It must call the operating system syscalls to inform that a program wants to do something to the common resource, and operating system either does it or allows a process to do it. But in controlled environment. If we access common resources without such protection, race condition occurs. What is a race condition? Race condition is a situation in which the result of a program depends on the scheduling of this program and other programs. Simply, a scheduler can interrupt any operation and give the control to other process that works on the same resource. So the result is unpredictable. This is a race condition. And system mechanisms for inter-process communication allow to avoid race conditions. So we can build a program which performs in deterministic way. This is a simple example of race. We have two programs, 1 and 2, and we have a common variable to those two programs. It is shared resource. Variable A is shared resource of those two programs. The program P1 loads the value of A to its accumulator. I assume only single register accumulator, increments the accumulator, and stores the results back to the variable A. Program P2 acts similar, but it decreases instead of increasing. Let us observe some sequence of operations. Program P1 starts. Variable A has some value X. Accumulator of program 1 is arbitrary. After loading variable to accumulator, we have the value X in A and in accumulator of process P1. After instruction 2, it is the accumulator is incremented by 1. But variable A keeps the old value, X. After step 3, we have the same value in accumulator and variable A, because the value is stored back to the variable A. And program P1 finished, so we run program 2. Number 4, loading A to accumulator of process P2. Its value is X plus 1. Decrementing value in accumulator is X, but in variable A it is still A plus 1. And storing accumulator to A puts X into the variable A. Everything works as we expected. But assume another scheduling. After instruction 2, some interrupt comes. We have X in variable A and X plus 1 in accumulator of process P1. We store somewhere the state of process P1 and load the state of process P2, because the scheduler now chose program P1 for execution after this interrupt. So we have step 4. We loaded A to accumulator of P2. We decremented it, and we stored the result to A. And program 2 finished. We come back to the program P1, which waits inactively. We load the context of program P1. There is one instruction to finish. We execute this instruction that stores the value X plus 1 to variable A. We expected that those two programs would leave the same value as it was before. One of the programs increments, the other one decrements. But interruption in this moment causes the results to be not deterministic, because it can be x plus 1 or x minus 1 or simply x. 3 possible results are in this example. It's because we can interrupt the sequence of operations on shared resource. The sequence of operations that we should not interrupt is called critical region. It is sequence of operation which, when interrupted, can lead to race condition. If we protect those parts of code with critical sections, the solution is safe. The question arises, is this sequence non-interruptible at all? It is interruptible. When we compare with program P3 that accesses different resources, not variable A, they can interleave freely. We only not allow to interleave instructions concerning the same resource. Because the interrupt was the source of our problems, we can say, oh, we have an easy solution. Let us disable interrupts. What is easier? By the way, it's not so easy, because disable interrupts instruction is typically protected instruction that can be run only in system mode. So a user cannot do that. But if we can disable interrupt, it is successful. It is not elegant. And sometimes it's not safe, because we don't know how many instructions a process wants to run in the critical section. Can it be 1,000 of instructions? Yes. 2,000, million, why not? And some devices are very sensible for disabling interrupts. In extreme situation, we can dematch the resource, the physical equipment, if we do not answer to the interrupt very long. So it is possible, but it can be not safe. And if we have many processors, another process can run in parallel. So disabling interrupt does not help. There is an algorithm invented by Decker. It's called Decker algorithm, enhanced by Peterson. So it's called a Peterson algorithm as well, in which processes can synchronize on entering the critical section. However, I will not teach you this algorithm because it works only for two processes, because it is based on giving the processor to another process in strictly defined moment in time. And in modern operating system, we have no such operation. Please give a processor to this process. A scheduler decides, not a process decides which process will be next. And we cannot synchronize more than two processes using Decker algorithm. So we will not discuss this issue. It is unpractical, I can say. Instead, the designers of processors invented some clever solution, some clever instruction. It is called test and set. The rules in this instruction are: first, some register appointed by the programmer is stored to some memory location, Z prime. Then another memory cell is moved to the register. And it is done in exclusive access to the system bus. That means that this instruction cooperates with system arbiter, bus arbiter of the computer, in a special way. If we perform the first access to memory, arbiter will not allow any other module in our computer to access the bus until we perform the second access. It is a special access to the bus for two consecutive transmissions. So it requires cooperation of a processor with bus arbiter of the computer. Oh. It performs those two operations indivisible. We have second processor that wants to access system bus between 1 and 2, it will be held up. The arbiter will not give access to the other processor between 1 and 2. In Intel processor, we have another version of this instruction. It is called compare and swap. Not test and set, but compare and swap. Why swap? Technically, it is performed such a way. A register value is moved to the temporary register, or here you have the property of this register, which is not accessible to the programmer. It is hidden register in the processor. Then memory cell value is moved to the register, it's number 2, and then temporary register is stored to the memory location. Effectively, this sequence swaps Z with R. This is stored here temporarily, Z to R, then temporal register to Z. That's why it's called compare and swap. When we abstract from the temporal register, we can just say that we swap the values of the register and memory cell. This instruction is lock exchange. Exchange in Intel is exchange two registers or register with memory location. And lock is the prefix that informs bus arbiter that we will perform two operations that should be treated indivisibly. I checked the documentation, and after making the slide, I realized that here lock prefix is to exchange is added automatically. That every exchange operation that concerns memory has implicit lock prefix. So even if you don't use this prefix, it will be done indivisibly. How to get access to some sequence of operations using test and set or compare and swap. Here I use this in Intel assembly language. So I use this lock exchange. Lock is not necessary, but it is on the slide. And this is an example, of course. I enter some value. I decided value 1 to the general purpose register AL. Then I swap the value of this register with some global variable G. And I test this value if it's 0 or not. When I stored this one to the global variable G, I got to AL the previous value of G. If it was 0, okay, I continue. If it was not 0, I jump to B and test again. So I execute instructions in the loop until some program enters 0 to G. Entering 0 to G is leaving the critical section. When some other process that entered 1 to G before me, because I got 1, it means that I entered 1, but it was 1. So another process entered this one before me. And when this process finishes critical section, it enters 0. I will enter 1, but read 0, and I can continue the critical section. Maybe I will return to the slides on kernel, because I have this situation explained in more detail. Okay. Here I have the same with some animation. What happens step by step. first assume that we have 0 in global variable G. We enter 1 to AL. We exchange AL with G. So now we have 0 in AL, but 1 in G. We test AL, it is 0. We do not jump, we continue. This is the situation when G was 0. For G equal to 1, we move 1 to AL. We exchange 1 with 1. We test AL, it is 1, so we jump to B. And again, and again, and again, until someone enters 0 to G. If the other task assigns 0 to G, I will not jump, I will continue. And the loop will be broken. So this sequence of operation is locking access to the critical section, and this is unlocking access to the critical section. Just moving 0 to G. And of course, two programs that want to cooperate must have similar sequence of operations. X and Y are instructions in the critical section, but they are both preceded by locking the critical section on the same variable G. Okay. Such a way we can get access to the common resource, and actually such mechanism is used in operating system kernel for exclusive access, for example, to kernel structures. Let us imagine a process started input operation from the disk. And interrupt comes. So the driver of the disk invokes in the kernel operation, please wake up this process. However, at the same time, a timeout that we set to this operation has finished. So when we are waking up the process, the timer interrupt comes, changes the current clock value, and checks what process has timeout, this process, and timer interrupt tries to kill the process because a timeout occurs. So at the same time, we have two operations invoked that operate on the same process descriptor: waking operation and killing operation. What will be the result? We cannot say. That's why the access to common resources in the kernel are protected by some synchronization mechanisms, like test and set, for example. Okay. What is critical section? It is a sequence of operations that must be executed in exclusive mode from the point of view of some resource. To do that, we must lock the critical section before we enter and unlock when we leave. These are the correctness conditions published by Greenhausen. They are conditions for the synchronization mechanism to be safe. First, only one process can be in critical section. Of course, 0 processes can be in critical section, but at most one. Any process outside which is not in the critical section cannot influence the process that wants to enter the critical section, I add, or which is in the critical section. We have not enough time, but you can observe the literature on the Pathfinder Mars Explorer. NASA sent Pathfinder to the Mars, and it started to operate. It left the platform on which it landed, then it stopped. The situation was because of the phenomenon called priority inverse. This is some subtle set of dependencies between processes which causes influence of the process outside critical section on the process that is in critical section. So it was wrongly constructed. Now, a few words of history. It was the operating system, the kernel of operating system, VxWorks, that is widely used for real-time systems. And NASA was saving money, so they did not elaborate their own operating system kernel. They just bought the kernel on the market. A researcher from Netherlands discovered this error, and he sent to NASA the letter that this kernel has the possibility of priority inversion. And they responded to him that they tested everything and everything is okay. What was the error of NASA? The principal error. In the very beginning of computer engineering, the famous researcher Dijkstra formulated the rule: using testing, you can find errors. So testing, the purpose of testing is to find errors. But you cannot prove the correctness of the program using testing. Every IT student knows about this, and when the student becomes the worker in the industry, he simply forgets about the rule. And I many times heard that people wanted to prove the correctness of software using testing. It's not possible. Luckily, they left the possibility to upload the kernel to the Explorer. It was not easy. With the speed of communication between Earth and Mars, maybe a byte per second or slower, but they managed to upload corrected kernel. Otherwise, this Explorer, the mission costed about $5 billion, and they would lost just those money if they wouldn't be able to upload new kernel to the Explorer. How this phenomenon works, you can read in the literature, priority inversion, and we'll return to our synchronization. Any process awaiting entry to critical section should be granted the access in finite time. It can be very long, but finite. In practice, very long is not enough. We cannot, on our PC, we cannot wait a year or 1,000 years for entering critical section. It should be done in some parts of second. Yeah. However, formally, we must guarantee that every process will get the critical section in finite time. In practice, reasonable time. Okay. So what are the manners of achieving this property? Interrupt blocking. It is successful on uniprocessor. If we have one processor, interrupt blocking is successful, but not elegant, as I told you. And it is not effective in multiprocessor. Then we have mechanisms with active loop of waiting using test and set or compare and swap, or this Peterson algorithm that I do not offer. It is only for two processes. And some mechanisms that suspend a process that cannot enter the critical section. So this process changes the state to suspend it. The scheduler does not choose this process. It just waits for another process to leave the critical section, and then our process can be resumed. Okay. But on a lowest level in the kernel, we cannot use the inactive waiting. Who will wake us? In the kernel, we can only use active waiting. And using active waiting, we can suspend a process. So inactive waiting can be used on a higher level of abstraction. And we have three such mechanisms. There are more of them. Three of them that we will learn is semaphores, monitors, and messages. Those two are called synchronization by variables because they use some value of some common variable. Like in test and set, there was a variable G, you recall. In messages, we do not use common variables because this mechanism is addressed for distributed systems in which we have no common memory. So we do not use common variable. Oh, this is return to interrupt disabling. We can skip. Peterson algorithm, we skip. Okay. Let us start with series synchronization mechanism, and simplest one among series mechanisms, it is semaphores. Semaphores were invented by Dijkstra, the same Dijkstra. He observed the movement of trains at the station. Because the railmen knew semaphores almost from the beginning of railway. But yeah, and the name of the device is semaphore in rail equipment. And he observed and he constructed a mechanism in software that operates similar to railroad semaphores. First, let us observe what Dijkstra observed. We have a common track. There are two tracks, and they join to a common track for some lengths. And this is the semaphore. Old semaphores worked such a way that they had two positions, up and down. When the train approaches semaphore, a driver observes the state of semaphore. If it's up, the train is allowed to pass. If it's down, the train must stop and wait. So this semaphore is up. And when the train approaches, the train, in old semaphores, not electronically operated, just the train moved some metal elements with its wheel. And this mechanism pulled a wire, and this wire lowered the semaphore. Now it's done electronically, but the rule is the same. So the train influences the semaphore. This is some sensor point of the semaphore, which causes the semaphores to fall down. And the train continues. The other train approaches, and the driver looks at semaphore. Oh, it's down. So it stops. He stops the train and waits under the semaphore to be raised up. When the first train left the common part of the track, the train, in the same way, just pushing some element, influences the V operation, which rises up the semaphore. Now, this driver sees that the semaphore is up, and he can start again. It lowers the semaphore for the second time because, again, the track is occupied. And here, the train influences the V point to rise up the semaphore. So we have two operations, P and V. Dijkstra gave them those two names, P and V, and he describes that P is for passeren. In Dutch, it is to pass. And wrigeven, which is to release in Dutch. Later, he changed his mind. He changed passeren to proberen. Passeren is pass, proberen is check, to check. It's better name, I think. Because here, the driver checks if he can enter the common part of the track. And verhogen, it means nothing because it is not a word. It is connection of two Dutch words, which I don't remember what they mean. So let us stay with wrigeven, which is to release. Okay. So what is the mechanism of a semaphore? It is a common variable. How we can establish a common variable between two programs that have not a single common cell? How we can establish a common variable between two processes? It can be stored in the file, but I think the better solution is to hide it in the kernel. Thus, it is a single memory cell in kernel. But if it's in kernel, we must call some syscalls to access this variable. And it is done such a way. We have two operations, P and V, or up and down, or signal and wait. There are many names. Operation V is always successful. It is because it is rising up a semaphore. But operation P is pulling down the semaphore. So we can pull down the semaphore always if it's up. If it's down, we must wait under semaphore, like this second train. Formally, when we treat the semaphore as abstract data type, we can say that increasing is always possible, but decreasing is possible only if it keeps us in the set of values of this abstract data type. So if we define that it is non-negative, then an attempt to decrease value equal to 0 is ineffective because it moves us out of the scope of this data type, which must be from 0, non-negative. The underlined part of this definition are important, all of them. It is shared because many processes can access this variable for synchronization. Non-negative because crossing 0 is synchronization point. We can lower, 5, 4, 3, 2, 1, 0, and no, not below 0. It is synchronization point. It's not negative. The operations are atomic because if two processes are performed P on the same variable, one of them, assuming that the variable is one of them can execute P, and the second one not, because it is 0. So if we allow them to run in parallel, then can both decrease the value, like in our example of increasing and decreasing, without some safety mechanism. So those operations are atomic to the process. There are binary semaphores and general semaphores. Binary semaphore is a semaphore that is used mainly for critical section control. It is 1 when the critical section is free. It is 0 when critical section is occupied. That's all. The attempt to raise the semaphore that is 1 is ignored. It stays 1. The general semaphore, we can say it is counting semaphore, because it tells us how many times we can execute given operation. If it's 2, we can execute this operation 2 times, performing P. So after it is 1. When it is 1, we allow once again to execute the operation. After this operation, it would be 0. If we try for the 3rd time, we cannot, because the semaphore is 0. So we can say it is counting semaphore. It counts how many times we can execute given operation. If it's plum stealing, and we have 100 of plums, we set the semaphore to 100, and each time we pick a plum, the semaphore is lowered by 1. When we reach 0, the plum number 101 cannot be picked, because the process stops when it tries to execute P on semaphore that is 0. After 100 operations of P, the value is 0, and 101st operation P must wait a year for a new plum. This is how a semaphore is implemented in operating system kernel. If you have a kernel that supports semaphores, we must offer 2 syscalls, P and V. Of course, we must implement a function to create a semaphore, maybe some additional elements, but here we see how P and V are organized. What time do we have? Okay. The semaphore is a class. Why a class? Because for me, it's no use to program in other language that object programming language, because we can connect data and operations on data in single class. So if I ask you to solve some synchronization problem during tests, you need to write a class. This class has a parameter. It is the initial value of the semaphore. Because the semaphore it is binary semaphore. It can start from 0 or from 1, whatever we choose. So it's initial value of a semaphore. This is the value of semaphore. It is integer, so we see that it is general semaphore. And this is a queue. This queue is a queue of process descriptors. Simply, every process that wants to perform P on semaphore that is equal to 0 is entered to this queue and waits until this operation can be performed. So operation P is check the value of the semaphore. If it's positive, decrease it simply and not more. If it's 0, enter current process to the queue and suspend the process. How we suspend the process? We change the state of the process from active to suspended. And that's all. And please think, if we stop here the process, what process will go out of this operation? The operation, this process that entered the operation stopped. So what process will continue? It's a very good question. Very good, because the process that called P disappeared. When we execute syscall, we are in kernel context, not in user process context. User process disappeared. It is just a data structure, user process, just a descriptor. So here, as I told you before, on end of every kernel operation, a scheduler is called. And here, a scheduler will choose another process to run. If there are not useful processes, an idle process will be chosen. So we cannot say that the process that entered P suspends. No, the process that enters P rebuilt itself to be a kernel process, and kernel process suspends the user process and chooses another process. Kernel process, not user process. Oh, it's very important to understand. And the operation, it is reverse of P. If queue of waiting processes is empty, we increase the value. Otherwise, we take one process from the queue and change its state to ready and add to ready queue. So we resume the process simply. And the constructor of this class is initial, is value becomes initial value. That's all. It is important to understand that this we can call to the scheduler in that point as well. But here it is not so important, because here we can enlarge number of processes to run. But here we can decrease number of processes to run, and it can become 0. Then what to do? The scheduler is the answer. Because if there are no processes, it chooses idle process. Okay, thank you.